Welcome to the second session. It is my great pleasure to introduce Christopher, and he's going to be talking about the CN project, which we've heard a little bit about already, but he's going to give us a sort of broader overview of the whole thing. Take it away, Christopher.
Thank you. Yeah, so in this talk I'll be telling you about this CN type system we're building, and it's a separation logic refinement type system for C, with the goal of proving safety and functional correctness of tricky low-level C programs. And so it's roughly in the same kind of space as other tools like Verifast or Jillian or the various Viper-based tools and so on. Our specific focus is system software, because it's sort of tricky to get right, but really important to get right. So just to remind you of a bit of context that you'll all be aware of, in the past decade or so, there's been a huge amount of progress in this area of system software verification, with big sort of success stories like SEL4 and Certicos, verified operating system kernels. But despite these big successes, there's still a fairly big gap between verified software and conventional software you find in industry and how it's developed. In that these verification projects, they're usually... No problem. These verification projects typically assumed idealized language or hardware semantics just to make the proof feasible at all. And often these verified systems were designed from the start with verification in mind rather than taking existing software projects. And despite all of that, proof and proof maintenance were extremely expensive. That was many person years of effort by highly specialized people. So in the CN work, we're sort of looking at this context and trying to see if we can do a bit better and somehow reduce this gap a bit between the two, in that we want to verify software against realistic language semantics and verify production software and try to reduce the cost of the verification. And the original sort of primary application we had in mind for this is this PKVM, this ongoing PKVM hypervisor verification project that's already come up a few times. Since then, there's this big burst project, collaboration between a couple of academic and industry sites, trying to really make proof using CN usable by people also other than us, other than sort of verification experts. And we'll see how it goes, but we want to try really hard to do this. And a big part of this story is to combine proof with testing. So we want to use the same CN specification language for both testing of rich separation logic assertions and proof, so that you can gradually move from testing towards proof. So that's sort of the idea. And Rini and Benjamin already gave an overview of this in their excellent talk. So if you haven't seen it, you should watch the recording for this. And in this talk, I'll just be focusing on the proof part of the story. And I'll sort of talk about 3 points. One is what we're doing about the C semantics, then aspects of the type system design, and if I manage time-wise, I'll talk a bit about some open problems we're looking at in our current work. So first point is C semantics. Anyone who's building a verification tool for C will immediately run into the problem that C is a terrible language with really complicated semantics. So no matter what Peter says, it's not a great specification language after all. So C has various kinds of undefined behaviors and implementation-defined behaviors. There's unspecified values. If you do any arithmetic, there's various kinds of implicit integer type coercions and so on. There's a long list of these sorts of complications. The bottom line is just getting this right in a verification tool that accurately reflect the semantics is quite tricky. So we don't try to do this directly inside the type system, but instead build on an existing semantics for C. It's called Cerberus by Kevin Mimarian and others, and that's a well-validated C semantics. And it works by elaboration, so it defines the semantics of C by translating it into this other language called Core, and that's a sort of functional-ish language with more straightforward semantics. And the idea is that the translation makes everything that's complicated about C, or almost everything, explicit in the output core program. So if we take this sort of innocent-looking increment function here that just increments I and returns, Cerberus will say the semantics of that is this core function here. And you can see the bits highlighted in colors that don't come out so well, but you can see a couple of things that Cerberus makes explicit that are tricky about C. So for example, stack local variables are complicated. You can take the address and pass it around. And so Cerberus treats them a bit like heap allocations, in that you have explicit create and kill and load and store. Thank you. Looks much better. So we have explicit create and load and store and kill for these stack allocations. And whenever the arithmetic would have implicit integer type coercions, Cerberus makes those explicit using these conversion functions. And well, if we have this I plus 1 here, if I is a really large value, then there's the danger that this overflows. And because I is assigned int, that will be undefined behavior. So Cerberus has some explicit undefined behavior assertion, which will raise an error of some kind if this check fails. And the point of showing this is just, this makes it really easy for us to build a C verification tool with a good semantics, because we can just incorporate Cerberus into the tool. So CN is effectively a type system for this core language. So given a C program, CN uses Cerberus to translate this to a core program that is the semantics of this code. Then there's some simplifying rewrites, and then CN is a type system for this core language implemented in OCaml, including the ownership reasoning. And for sort of refinement typing and other bits of proof automation, we use an SMT solver. Previously just Z3, now also CVC5. So that's sort of roughly how we deal with the C semantics. I should say you should be asking questions along the way if there's anything. Okay.
I know you mentioned you were moving towards these vectors, and the core elaboration mentions like bound checks that are integers. How do you handle that?
We've slightly adjusted the core elaboration to remember a bit more structure that's present in the original C program, so that somehow combines this aspect, this conversion, and these assertions, so that there's enough information present in the core program to give precise bit vector types, even though core before this was phrased in terms of mathematical unbounded integers.
Defer this to later. When I love this idea of using the Cerberus as an IR, as it were, but it seems like one catch is when verification fails, the programmer gets to see the Cerberus and not the lovely function up at the top.
So definitely, we're putting a lot of work. We're not showing the core program. We have to put some work to hide it and report source locations that make sense in terms of the original C source. And probably we have to do more of this work to make it actually good. Right. So that's the C semantics. Then I'll talk a bit about some aspects in the type system design. And the main challenge here is this sort of obvious tension between the expressivity we need and the automation we also need. So we're looking at complicated production system software that does tricky low-level things, and it relies on complex correctness invariants. So we need a sufficiently expressive logic to be able to specify these things. At the same time, we also need proof automation to make this usable at all. And one would like everything to be fully automatic ideally. Our worry is that with fully automatic verifiers, one might have the danger that if that the proof might be the proof automation might behave unpredictably. So an example would be you have something that's working, but you have to adjust the specification a small bit to strengthen it, say, and suddenly the heuristics fall over, or the SNP solver starts spinning forever because it got just a tiny bit too hard. So that's sort of the worry. So we want to try to do predictable proof automation. We want to do that by just slightly carefully restricting the expressiveness of the types, and trying to stay in the decidable SMT fragment for the proof automation. So, and for doing this, we're building on the work on liquid types. So here's a tiny example just to give you an impression of what that looks like. It's the same increment function from before. And if we run cn on it, then cn says no, because without knowing anything about the I, we don't know that this won't trigger this undefined behavior assertion about the signed int overflow that we saw on the previous slide. So cn gives a type error, and the user can fix this by putting a precondition that constrains I to be sufficiently small, and then we'll have a post condition that says I is incremented in the right way. And that's sort of the C-like syntax we present to the user. Internally, this turns into some more sort of sensible-looking maths. And the point of showing this is mostly to say this is not anything new we're doing. We're building on Ranjit and others' work on liquid types, and they figured out a way to do this by decidable quantifier-free SMT solving this sort of verification. Basically, type checking turns into forward symbolic simulation, and along each control flow path, we check that the absence of undefined behavior and that user-specified assertions hold.
So how would you handle something like that Fibonacci example that I showed, where you need in the middle to do a bit of mathematical reasoning?
I had to miss your talk.
Okay, so I can explain it to you quickly. So suppose in order to prove that there is no overflow, I need to do a little bit of, I need to write a lemma somewhere. I need to show that, from my precondition and some other considerations, this overflow is not going to happen.
Yeah. So I'll come to this on a slide later, but yeah, generally the idea is certain definitions or certain assumptions that would break decidability, we don't hand off to the SMT solver, and the user has to fill in the gaps with function unfolding quantifier instantiation, and in the sort of worst case, lemmas when inductive reasoning is needed. So you can put them sort of inline as magic comments in the source code. I'll show an example of this later.
In the lemmas? Okay, I'll wait for your example.
Pardon?
I'll wait for your example.
Okay. Other questions? Okay. Right. So on top of this, for reasoning about memory safety, we need some notion of ownership. And what we do is we've given CN separation logic resource types. So those are first-class resource types, as inspired by Amal and others' L3 type system. And the idea is, so resource types are sort of types in their own right, which means we get something slightly more flexible than you get with Rust ownership types, where ownership is tightly coupled with the pointer itself, which is useful for things like dealing with pointer aliasing. Here's a tiny example of ownership or a resource specification in CN. But before we look at the details, let's just look at how you would say the same thing in separation logic first. So here's an increment function again. Now it works with a pointer, so it just increments the value under the pointer. In standard separation logic, you'd probably say something like this. At the call side, before you call this increment function, you need ownership of p for this to be safe. So you'll say, okay, there exists some value v such that p points to v, and v has to be small enough for this to be safe. And afterwards, we still have ownership. P points to some w, that's v incremented by 1. The reason for showing this is, in order to abstract over the values the pointer points to, we need quantifiers, these existential quantifiers, but arbitrary use of general existential quantifiers breaks reliable inference. So we have to be careful about this. So what CN does instead is that it has some sort of carefully restricted, syntactically restricted form of existential quantifiers with this take notation. So in CN you'll say this, and that's just equivalent to this here. We'll say in the precondition we take ownership of P, and this resource, it has an output which is the value represented by the resource in memory. So we introduce the name V for it, and it's the same V as here. And we can say, okay, V must be sufficiently small. And we can do the same in the post condition to relate the W, which is the state of the integer after the execution, to the one before. So it's the same thing, just syntactically restricted in a way that's useful because it means specifications like this one here that break inference, you just can't express it in the syntax. So here's another weaker specification for increment, and it's also a valid specification, just a slightly useless one. So here we say, in the post condition, there exists some Q, so we forget that it's the P that has the ownership. There exists some Q such that Q points to W. This use of the quantifier would break reliable inference because any points to lying around in the proof context would satisfy this. So we need some kind of backtracking to check specifications, which we want to avoid to get this sort of predictability. So again, the idea is the resource claims ownership and has as its output the value represented in memory at that location. And to sort of take this to the logical conclusion, for user-defined predicates, they end up looking a bit like function definitions. So if we take a linked list example, so a linked list node has a value and the next pointer, then in separation logic you say something like this: an int list predicate takes a pointer and a mathematical list that that pointer represents, and one of two things has to hold. Either the pointer is the null pointer, in which case it has to be the empty list, or we take ownership of the head and the tail of the list, and the mathematical list is the cons of the two. Sort of the obvious thing you do in separation logic. In CN, the corresponding definition looks like this. So we have something that looks a bit like a function. This resource int list, it takes a pointer as an argument, just the pointer, and it claims ownership and returns a mathematical list of integers as its output. And then the body looks a bit like a list traversal. So if the pointer is null, then we return the empty list, and otherwise we again take ownership of the head and of the tail and return the cons of the two. So again, that's just part of the same story of making these resource outputs work in a way that we hope looks appealing to software developers. Well, we still have to find out. And if you look at it, you can also see that this hints at some computational interpretation, which is useful for the testing story, although making this work in practice is then still really tricky. So, yeah, already said these things. One other thing to mention is we have this if-then-else structure rather than general disjunction, which helps with avoiding backtracking, and that's something refined C does in the same way. Yeah, sorry.
If you're interpreting these predicates as code, eventually also, are you concerned that operations and pointers like this, that comparing two pointers for equality, that's undefined behavior?
I mean, concerned only insofar as it might be counterintuitive to the C programmer, who hopefully knows to be more careful with it. So, I mean, this is, actually, sorry, there's two aspects of this. One is, we get to choose what the semantics of the specification language is, and it has to be something, I'll mention the memory object model later, but it's something where you have to be a bit careful about pointer equalities. Still, we pick some semantics that isn't the same as the C semantics for the corresponding operation. So that might be a problem for, as a sort of, it might be a user interface problem, right? The gap between the two. The other question is what we do in executable testing, and it's something we've decided not to be careful about so far, but we might have to in the future.
I'm curious if this language of executable predicates, if that's something that's worth studying as a thing in itself. Is that like is that something you can sort of relate to separation logic in a kind of?
Yeah, I mean we have this equivalence, and maybe there's something interesting to find out. Also, I mean, it's something Peter mentioned previously in this workshop, whether we can make this, if we extend the expressiveness of the language, whether we can maintain a nice correspondence, a nicely sort of executable looking specification language. We haven't thought about it enough yet.
You have some algebraic equalities between programs in on the rights.
Sorry,
the specification that you have on the right, do you have interesting algebraic laws about?
Maybe. I haven't thought about it yet.
I would say that in a slight sense, L3 is already showing the correspondence. Do you agree? Right, because there's capability threading going on as first-class capabilities being threaded through the program.
Yeah.
You're representing those capabilities as points to expressions. And the L3 paper showed this semantic model of L3 is basically a model of separation model. So maybe there's a hint of correspondence there already.
You mentioned that this computational way of writing down the predicate is useful for the testing story. I was wondering if it's also useful for inference. Like, is this compiled to some sort of formula, or when you process a take int list, do you interpret this then?
So it's not compiled to some formula. Yes, it's useful for inference, and I should have said the reason we arrived at this is thinking about inference, and then it turned out that those restrictions are also useful for the testing. One thing that's so CN's resource inference will try to repeatedly unfold these, and having these top-level if-then else's, for example, is useful because it means without trying any sort of backtracking, without going into the inside of the predicate, CN will check, can I prove that the point is definitely null? If so, I know how to unfold it. Can I prove that it's not null? Then I have this, before looking into the predicate. And that's useful for inference, but yeah.
Have you come across situations in which the version on the right ends up pixelated and you regretted it and you wanted to use the version on the right instead?
So we've run into not quite. Maybe you can create examples like this. I'm not quite sure. We've run into a slightly different problem, but where the current shape is a bit too restrictive, which is if you want to, when you have the pointer, you might want to claim ownership here and then switch somehow, like you say, you have an owned of something and it gives you some return value, and then you want to write an if then else that depends on that value, and at the moment CN won't let you, even though you can express this. I mean, it won't stop you from writing a predicate that satisfies this. Just you have to do mutually recursive things or whatever. It's so we want to extend it while keeping inference and checking working the same way.
I'm a little confused with the functional notation in predicate apropos cyclic lists. So with the ownership, the predicate presumably fails if the list is cyclic, because I can't get ownership at the cycle point. Is that right? So the predicate has a Boolean semantic as well as the return list. Maybe I'm just reacting to the syntax there that returns a list, right?
I think I am not following. So for cyclic list, you'd have to write a different predicate from this one.
So this one will be false, not undefined. It'll be false, is that right?
So I mean, this will only be satisfiable by non-cyclic lists, because each owned you've already claimed has to be disjoint from any owned you claim later.
The usual one.
Yeah. So it's not different from standard separation logic in that sense. And you'll have to write a fancier predicate for cyclic lists. That, I don't know, you remember some sentinel load and you have to check that you don't claim that twice.
Do you have a way of specifying pure conditions in a way that CN knows it's pure? Because, for example, if you want to say that the linked list, you want a predicate for a sorted linked list, right? That's a bit difficult here. You don't have quantifiers, so you would have a recursive predicate, I guess, that would say every node is further or something.
So we have some quantifiers. Yeah, probably the way you talk about sorted lists is you write. I mean, you might just do the recursive thing, right, where you talk about. Not sure. You could remember the things you've already claimed as part of the predicate. Say every new thing you claim has to be bigger than the previous, say. But probably what you do is you write this as a linked list predicate, and then you'll have on the side a pure side condition that phrased using a recursive specification function that says, and it's sorted.
So my question is more, do you have a way of saying in the syntax, the state takes spatial resource? Do you also use take for pure things like it's salted, like take salted equals something?
Oh, I see. I mean, you can just put an, there's a yeah, this example doesn't show it, but you might say assert and then say something about, I don't know, the node and the tail, say. So you could say, you could have a pure condition as part of the cons case and say the node's value has to be smaller than the first element of the tail, say, and then recursively that gives you the thing you want. You can also wrap a pure assertion in a predicate, but you probably don't want to. Okay. So the last point, there was already a question about this. So we have these carefully restricted existential quantifiers. The last point about type system design is this one. Even with that carefully restricted, even with those carefully restricted quantifiers, we of course still run into the problem that I mean this tension between expressiveness and automation, right? We wanted to stay in the decidable SMT fragment, but limiting specifications to just decidable logic is too restrictive for the kinds of specifications we're looking at. And so what we're doing is we're sort of carving out a particular part of the reasoning that you can do in the automated, in the decidable SMT fragment, and then we're doing that automatically, and the rest the user has to do manually. Where the hypothesis, and this is a bit different compared to other verification tools, the hypothesis is that maybe a clearly delimited sort of envelope around the automation is more usable than best effort but stronger automation. Is the idea, and we don't know yet whether that's true or not. We're exploring that. In detail, that means users can write recursive specification functions and all quantified assertions that easily get you outside the decidable fragment. So those are not handled by the SMT automation, but the user has to then do manual unfolding of recursive functions, quantify instantiation, or when inductive reasoning is needed, lemmas that can be exported to ROC. And I think I probably won't have time. I had an example of this on the slides, but I can show you offline if you're interested. So that's sort of the type system design. In our current work, we're looking at a couple of problems. The first one is, from Cerberus, we get this nice C semantics for free, and that is true for almost all of C, with the exception of the memory object model that Cerberus handles differently, not inside the C to core elaboration, and so CN doesn't get it for free from Cerberus, and we have to do tricky work on our side. And so Dhruv is at the moment, or has maybe finished by now, extending CN with sound typing logic, I mean sound with respect to the VIP memory object model to get the semantics of pointers right. Then expressiveness already came up as a problem. I mean, we know that for looking at trickier parts of PKVM, for example, we need to extend the specification language. The moment CN only handles sequential C programs and specifications are first order, and we need to handle concurrency, and we'll probably want some form of user-defined ghost state, and eventually we'll want to handle relaxed memory concurrency, and probably for making it nice to write specifications, we want polymorphism and maybe higher order specification functions and so on. So obviously those are tricky to get right for proof automation and for checking. So we're exploring at the moment how much of some of these things we might be able to have while retaining reasonable, predictable automation and runtime checking. And I had 2 more points, but I think maybe we're running it. Maybe I should ask if there's any questions because we're running out of time. Should we? Questions? Yeah. So I don't show what the ROG output looks like.
4 seconds.
Yeah.
Or, I don't know what. Peter's still grinning. Peter still has a smile on his face.
I see.
over
Yeah,
lunch.
I'll show you offline.
I would also like to see that.
Uh-huh.
Okay, thank you.
Yeah.